Today I want to talk about one of these key environmental disasters, which is nuclear disasters, right? Now again, we're going to touch on war in a little bit. We're not, as we said at the start of this class, we're not specifically talking about war. That's its own category, but it does play into some stuff. But I want to start with some background. So as I talk about in my intro to this topic, and this is something for you all to pay attention to as you get older and move into your careers. So black swans. Has anybody heard black swans before this or before we started talking about it in this class? A few people? Yeah, okay. So the idea is black swan. When you go to the lake or go to the pond, most of our swans are white, right? And so it is true that there is such a thing as a black swan, but it's sort of rare, right? It's an unusual event. And the idea is, historically, the idea is a black swan is something that, oh my gosh, I couldn't have predicted it. It's out of the blue. It's totally unusual. It's not normal. It's not my normal experience going to this wetland or this lagoon or this lake or whatever. And so, I can't predict it. And a lot of times it's been used in the context of things like market fluctuations, the stock market, or some global event that no one could have predicted. Then this thing just came out of the blue and changed the world, right? Yeah, I suppose, but much more often these things that people portray as black swans, and they're usually the folks that should have known about them ahead of time, but they kind of are trying to say, hey, not my fault. Who would have guessed, right? So we saw some of this with Hurricane Katrina, and some of the officials saying, who could have guessed? Well, actually, we all did. We modeled it. We had, we were trying to clang the warning bells. And so perhaps a better analogy is a gray rhino, which is another sort of phrase that people have started using in the last several decades. So another example might have been the pandemic, right? Who would have possibly guessed a global pandemic could have, well, let's see, Hollywood, NIH, WHO, all of our doctors. So the idea is with a gray rhino, and the idea is we're sort of camping out on the grasslands in Africa or something like that, and someone could have said, how possibly could a gray rhino have run through our camp? Well, of course, dude, if you knew the ecology, if you knew the system, if you knew the setting, you would know that maybe rhinos are around here before we drove them to extinction. Maybe the rhinos are around here, and maybe they would, maybe they're a threat. Maybe they're not happen every minute or every day, but still it's something that's totally within the realm of possibility and something we should probably prepare for. So many of these disasters that for political reasons, some people would have you believe are a black swan are really probably more a gray rhino. And I would argue that the stuff that we're going to talk about today, at least these nuclear disasters, are more of this gray rhino variety, not the black swan. Okay. The other thing I think is, as we've all been witness to in the wake of the pandemic and our wildfires and stuff like that, we sometimes have some perspectives that are grounded in our historic experience, and we kind of think things change gradually. Like, let's say in the fall, the trees have leaves, and then eventually starts the guys that are dioecious, they sort of start to drop some of their leaves, or actually the leaves start to get a little brown, and they get a little bit more brown, they get a little orange and a little bit yellow, and they start to drop, right? So that's how things change. Yeah, but we can also get a lightning strike that strikes that tree, or a car that crashes into that tree and knocks that tree down, and all of a sudden, now all the vegetation is gone instantly. And in recent years, when we have things like 24-hour satellite surveillance and things of this nature, we can actually see some of this dramatic change unfold right before our eyes, or in real time kind of thing. And so it's important to, when we have these situations, these potential environmental threats, these potential things of environmental concern, that you get into the habit of shifting your perspective, right? So put a mirror on there, look at it reverse. So my father is an oil painter, and he used to paint all his paintings in, he's old now and doesn't really do much painting anymore, but when he used to paint all the time, he would paint these big, large canvases in one fell swoop, or for the most part in one fell swoop. So he would paint for 24, 36 hours straight, nonstop. And when you're looking at that canvas for for 10 hours, 12 hours. You start to kind of like, what is that? So what he did many years ago is he bought this old Victorian mirror. So a really pretty mirror, like, as tall, like 6 foot tall. And he put it on he made a friend of his who built ships, make a sort of nice custom wooden roller on the bottom of it. And he would position that on the other, so he'd be standing on the right side of the painting, he'd position on the left side of the painting. And he would paint for a while, then he would stop and he would look into the mirror and it would reverse the whole painting. And so it gave him a fresh perspective. It was like, okay, the composition is all messed up. I really need a light area over here or a dark thing over here or whatever the case may be. And so it's important as you guys go into your careers, when we get to things that we sort of think we know about, always a good idea to every once in a while put that virtual mirror up and read a different article, read an article from a different news source, read something. But let me hear some other take on this situation, and that is usually really, really key for making sure we're not missing something. Okay, so. So many of these let's call them gray rhino events can crop up, and it's amazing how fast they can change our perspective. And you were all witness to when the pandemic happened. All of a sudden, everybody within a day or so, everybody was staying home, or within a week or so, everybody was staying home, and everything got virtualized. And so these events can be dramatic. So this is Sputnik over here. So this is what helped catalyze the modern global interest in research and science-based stuff, peer review, state-funded science. The current administration has basically destroyed that, unfortunately, and we've changed the world in many different ways in the last few months here, but one of which is we don't seem to care about science or education anymore, and we also don't want to fund that anymore. But this was all birthed by Russia getting this first satellite up in space, and then the U.S. feeling we're secondary, we're behind, we got to keep up. So things change on a dime. We talk about the Cuban Missile Crisis, which was the closest we've ever been to nuclear war in our planet's history. It turned on a very lucky few choice of events, I'll just say that. 9/11, Deepwater Horizon, Challenger explosion, all these things. One little event can actually really strongly change our perception as to what is safe, what is acceptable, what have you. Okay. The other thing, since we're going to talk about radiation here in a second, is radiation can seem very scary, right? We typically can't see radiation. So it's an invisible thing, it's in the dark, we don't know. And things that are in the dark tend to scare us and tend to make us really uncomfortable. Radiation. Okay, as a brief recap of what we led into with this, we have fission and we have fusion, right? So fission is the breaking apart of things. The fusion is adding together of things. And when we do that, we can produce ionizing radiation. Ionizing radiation are, and this is the whole particle wave debate you might remember from physics and all that good stuff, but suffice it to say, ionizing radiation is radiation of a sort that can strip electrons from other from elements. And when we remove those electrons, we call that ionization. And when we have ionizing radiation to you and I, that can cause a lot of damage to biological tissue, other structures as well, but in the context of today, to biological tissue. So first and foremost, it can burn us. It can just, like putting your hand in a fire kind of thing. It can oxidize stuff or help oxidize stuff. It can absolutely screw up our systems in our bodies, screw up our metabolism. And it can also, longer term, it can nuke some of our DNA such that our DNA doesn't function properly, starts generating these weird proteins, doing strange things, right? So that the next generation of cells might be mutated. All those things are possible with ionizing radiation. Where does it come from? Now, first and foremost, we have background ionizing radiation that we're just living in, right? So you can get a little bit of that from your television, you get a little bit of that from your microwave, etc. Oh, why can't you see that? What happened? How come you can't see that? Wow, that's weird. I can see it on my screen. You guys can't. Oh, there it is. That was weird. That's a real black swan, because I didn't know that would happen. But okay, so we have background stuff, but we also have background stuff that come from outside of we humans, right? So things like certain ores. We have some types of granite and other things can release things like radon gas that could get out, or uranium, things like that. And cosmic rays, so just coming out from the universe into us. So one of the big challenges for our astronaut friends and cosmonaut friends and all those folks that are up and about outside of Earth's atmosphere is not only the fact they can't breathe and there's no pressure and all that kind of stuff, but also just the radiation in space. So our Earth, our atmosphere and the electromagnetic encapsulation that happens because of our magnetic field actually shields us from a lot of that radiation. Ozone helps as well. So one of the challenges with the astronauts go up in space, they also have to think about radiation protection in addition to the temperature and everything else. Okay, so ionizing radiation, different sources. Okay, good. All right, so when we talk about where we're speaking of in the electromagnetic spectrum, we're talking about stuff that's over there on the right. So this more higher energy level stuff. So beyond the wavelengths that you and I see with our eyeballs, for example. Okay, when we have a radioactive particle that undergoes radioactive decay, it's going to change to a different particle and release some amount of energy. There's three broad categories of energy that we get, and we refer to them as alpha, beta, and gamma in terms of their radiation categories. Alpha is actually a helium particle that flies out, so like a physical thing. The beta radiation is basically an electron, and gamma radiation is basically a photon. Alpha radiation is very easy to stop. So with a regular piece of paper from your backpack, you can stop alpha radiation. With your shirt between your skin and the atmosphere, you can stop it with that. So alpha radiation, very low ability to penetrate objects. Beta rays will go through that and go into you. But with your thickness, with most of our, with our human thickness, a few inches, a foot or so, that's enough to take care of the beta radiation. Gamma radiation, though, is the most problematic, and that's the one that would go through the paper, no problem, go through you, no problem, etc. And we need something that's much more dense than you or I, or a paper, or a backpack, or jeans, or whatever. We need actually something like lead, some very, very dense material. Okay. As this material decays or undergoes radioactive decay, some things decay faster than others. And so one of the ways we typically communicate this is with a so-called half-life. So if I had 10 grams of this material, how long would it be for me to have only 5 grams of this that's still radioactive? That's the idea, right? And so half-lives vary over many, many orders of magnitude. So we can have something from a few days, like iodine, like radioactive iodine, or it could take years, say like cobalt, or it could take thousands of years, like carbon, and we actually utilize this in terms of our so-called carbon dating, when we're trying to figure out how old a fossil is, or some relic in the soil or something. And we can get up to million or even billions of years with some of our more unusual elements. So the half-lives are highly variable. And related to this is this idea of isotopes, right, or isotopic theory. And so the idea here is an isotope is the same kind of element, but it has a different number of neutrons, so the neutral charge on the element. All elements can potentially have isotopes, but we really talk about in the context of this, in sort of disaster management and stuff like that, really two main types: stable, which are things that aren't changing, and unstable, which we usually refer to as radioactive. So they're unstable. The reason they're radioactive is because they're like, they're falling apart, basically, right? And the falling apart is that energy that comes off of them. We can induce isotopes by screwing with some elements. And we can generate our own radioisotopes. In fact, we do that for things like medical to generate the material that we want to, say, put a tracer study in you to look at how your blood is circulating around, or if you're having a heart attack, or that kind of stuff. And it is true that some things, like uranium, is only unstable. So if we waited long enough, eventually all the uranium would be gone in our ore deposit, or in our state, or in our planet, or whatever, if we're not adding new energy into the system. Hydrogen, just for completeness, since you guys might have had chemistry a while ago, for completeness, hydrogen is the only element that we actually give special names to the isotopes. Everything else, we just call it the element's name and then a number. So with those isotopes, and that's important for nuclear energy, particularly fusion. And so we call regular hydrogen just hydrogen. We call one when we have an extra neutron in it, we call that deuterium. And when we have two extra neutrons in it, we call that tritium. And so this is a key element of some types of, and so this is where people say, for example, if we get fusion working, we can power this whole city with a bucket of water, right? So people are talking about things related to this. Okay, all right, so that's a little bit of background on the radiation. The last little bit is, let's just talk about what it does to, or what the potential risk of radiation is to us. So that means we need to talk about the units. How do we measure ionizing radiation? And so we have Becquerel, which is the international scientific unit of radioactivity, of any radioactivity. And then we can talk about the international scientific unit for ionizing. And that, again, that's really what we care about. We don't care about the theoretical radiation. We care about the kind that's potentially damaging to biological tissues. So we talk about a gray. And that's essentially 1 unit of ionizing radiation. And very commonly we talk about Sieverts, which is the unit to measure effect on living organisms. Okay, so Sieverts. And so all these are units, but really it's mostly, if you read the literature, you'll hear like Sieverts, because that's what people are measuring. Like if you and I go into a radiation zone, that's what we're going to be checking how much have we gotten in that context. Okay, so for context, what are we getting? So if you eat a banana for breakfast, you're going to get about a little bit less than 100 nanosieverts of radiation from that banana, because the banana has a lot of potassium. Potassium in there has a little bit of radiation in there. So no big deal. If you walk through the airport screening where the thing, you have to put your hands up, right? You go like this and you freeze for a second and the door kind of woof, woof, woof. That one is going to give you about 250 nanosieverts of radiation. If you go to the dentist this week and they say, we got to do a set of x-rays. We haven't x-rayed your teeth this year, so we're going to do that. That's going to give you somewhere around 5 to 10 microsieverts. The folks that were closest to Fukushima when the nuclear meltdown started, the estimate is something on the order of about 60 to 70 Millisieverts is what they received. Again, these people are really close right when it's just sort of was unfolding. If you're a smoker, now this is based on, I don't know what e-cigs are, or vapes, you kids these days. This is from regular old school, cancer stick smoking things, right? So, so if you smoke a pack and a half a day, you're getting on the order of 160 millisieverts. The folks that went into Fukushima to help in the immediate hours and days after the disaster happened, just because we had to contain stuff and we needed somebody in there. Those folks, the highest recorded that they ever got was 670 millisieverts. If you had, so these are all nano, micro, milli. If you had a full sievert, right, so that's what this one is, 4 to 5, you have about a 50% chance of not seeing it to the end of the month, that you're just gonna die pretty quick. So that's a little bit about the sense of scale for this, about this exposure. Does anybody know where this is? Any guesses as to where this might be? These are all crater, 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 crater. Ooh, Rocketdyne, good guess, but no, but good guess. Area 51? Close to Area 51, very close to Area 51. Mojave. Not the Mojave. This is the Nevada nuclear test site. So this is about 45 minutes north of Vegas. So this is where most of the US nuclear testing historically has happened. So so we used to, in the 60s, we used to go to places like Bikini Atoll and set off bombs in the water, in the air, etc. We also set off bombs in the air on ourselves in the desert, right? So at this place, for example. So there was all kinds, I probably should have put a picture in here. You guys might have seen these pictures, like all the Rat Pack, they're out there gambling in the 60s, smoking and drinking, and then people are like, hey, there's gonna be a test. And they walk outside at midnight or 1 in the morning or something, and the sky lights up. So we did that to ourselves. Starting in the 1960s, one of the things the Kennedy administration helped negotiate was this atmospheric nuclear test ban treaty. And so at that point, all the signatories agreed to no longer test nuclear weapons out in the open. So what we did is we went to this particular place in the desert, and we started drilling down underground and detonating these nuclear bombs underground. So the engineers could see how big the blast was and all this and that, but it didn't make a big giant mushroom cloud. And so what you're looking at, each of these pockmarked holes is essentially a collapse of the ground, because we blew up a giant cavern or liquefied a giant cavern underneath that area. So if you guys want, when we take a break, I can tell you stories about this place. But I learned about ionizing radiation when I went here. And there's a whole long story about that, but to help with some research and some monitoring. And so where I first encountered this was this security company, which was very poorly cloaked. They were basically CIA security contractors. And when you would enter, so when I went, so President Clinton stopped all nuclear testing. He said, no, we don't need to do this. We can do simulations, and we need to be phasing out of the production of nuclear weapons from a sort of global security perspective. And so when I went up, there were no tests going on, but they all thought President Clinton was not going to get reelected, and that the new president was going to come in and reactivate it. So they kept everything going, even though there was no nuclear testing going on. And so one of the things they handed me, I don't have a picture of it, I can tell you why later, but basically they gave me a badge that looked like this. This is what it looks like when it's opened up, but mine was closed, a big heavy thing, and you clip it on your chest, and you're supposed to keep it with you the whole time you're at the nuclear testing site. And so when the guy handed it to me, I was like, what's this? And he said, this is a radiation sensor. So it's going to tell me how many millisieverts or microsieverts I'd be getting. I'm like, cool. And I was looking at it, and it just looks like a piece of big plastic, right? It's kind of heavy piece of plastic with like a name badge or a, kind of thing. And I was like, oh. And I'm looking at it, and it just looks like, I don't see any moving parts or anything, right? I don't see any batteries or any lights. I'm like, ah. So I was like, well, how does this work? And he goes, well, this is going to tell us, this is going to let us know how much radiation you get when you're here. And I was like, oh, okay. And I'm flipping it over. And I was like, yeah, but I don't see the readout. He goes, oh, you give it to us when you're finished here, you give it to us and then we'll take it. I was like, oh, really? He's like, yeah. And I said, well, so how does it work? He said, basically, it's a piece of film, a photographic film inside, right? And so you and I are used to taking well, you're not used to, you guys have camera phones now, but back in the day, we'd put film in a camera, and I'd click the button, and a little opening would open, and that light would go inside, and it would hit that film and have a chemical reaction, and from that, we would get, light, dark, pictures, etc. And so that was from the kind of spectrum of light, of radiation that you and I see with our eyeballs, but it does the same thing with other radiation. So even though this is in a little black box inside my badge, it was sealed up, it would perceive the radiation. And so I said, oh, that's cool. I said, so I give it to you, then you tell me how much radiation I get? And he goes, no. I'm like, well, how do I know how much radiation I get? He's like, that's classified. It's like, well, how do I know if there's a problem? He said, if there's a problem, we'll call you. So I never knew how much I got, but I think we got a lot. But anyway, so that's measuring radiation. The other thing when we talk about nuclear power is this idea, and we cannot disassociate. This is true for all of our disaster conversations. Hopefully you guys have seen this with all the different stories. But the perception is a huge part of the story. It's a very real part of the story. And so in the case of nuclear power is wrapped up with nuclear weapons, with the slaughtering of our fellow beings. And so the only country in the world to ever use nuclear weapons on other humans intentionally is us, right? So we dropped 2 on Japan that brought an end to World War II. So at Hiroshima and Nagasaki, and these are the bombs that we built that were dropped from conventional planes back then. On the right is the wake of the town of Hiroshima after the blast. It's estimated that the folks that survived Hiroshima, so many people died and were just either instantly killed or died very soon after. But for the folks that did survive, the estimated average was something on the order of 200-ish millisieverts. And if they got only that amount, they were okay. There were survivors that definitely lived and survived many years that had as much as 1,000 millisieverts, but those folks clearly had elevated cancer risk. So they might have survived, they're okay and everything, but give it a year, 2, 4, 5, 10, 15 years, and they had significantly elevated cancer risk from that mutagenic aspect of the ionizing radiation. And again, it might be hard for you guys to understand, but this was a huge thing. The fear of radiation, the fear of nuclear war, all that stuff was just tremendous. It was perhaps most typified by Godzilla, which you guys might think of as sort of a quirky kind of, but you should go back and watch the original Godzilla. So the original Godzilla is a Japanese-produced movie, and yeah, it's a monster movie, and yeah, there's a guy in a costume walking through a fake city. But at the heart of it is this fear that using nuclear weapons changes the world somehow, right? So it changes the world, and the shtick is that it causes some problems in the natural world, and it wakes up this giant beast, and this beast comes and then wreaks havoc, and we have to shoot jets at it and all that kind of stuff. But fundamentally, it was made as an anti-war movie, which we now perceive it as some kind of cartoon, farcical thing. But that really speaks to, and the power of Godzilla is one, because of the quirkiness and all that kind of stuff, but also because of the real fear the underlying fear that it spoke to in our culture at that time. Okay, jumping forward to more modern times, this is the current, or one of the currents, a scale of events. So this is the IAEA, the International Atomic Energy Agency. This is an independent body that's staffed with UN folks and folks from around the world that acts as the third party, that acts as the entity that helps us work to prevent nuclear holocaust, nuclear risks, nuclear accidents, all this kind of stuff. And so in 1990, they introduced what they proposed was a clearer rating scale for nuclear accidents, for nuclear disasters. And so they propose a 7-point scale, so it goes from 1 to 7. It's intended to be logarithmic, so like our earthquake scale, right? So it's not just 1 unit worse when we go to 2, it's exponentially more problematic. The problem with this scale, it's useful for us as we sort of as we're sort of entering the field to sort of get a sense when we don't know about stuff. It's meant to sort of roughly put stuff into different bins for us, but it's only assessed after the fact. So it's not particularly helpful as, you know, a disaster is unfolding or that kind of thing. One of the problems is that it mixes together the magnitude and the intensity. So it mixes together the size of the impact with how much radiation is released at any one particular point. And so they would refer to the first 3 as if we had an event, that would be a nuclear incident. If it is a 4 or higher, that's a nuclear accident. And so we obviously have many number 1s, fewer number 2s, and so on and so forth, and very few, thankfully, of those high numbers. So of the major, so the worst of the worst, the number 7, would be a major release with widespread impacts, widespread health impacts, widespread ecological impacts, and need lots and lots of response, lots and lots of countermeasures, lots and lots of moving people around, lots of introducing structures. And so 2 examples of that would be Chernobyl, which is 1986, and Fukushima. All right, those are the 2 worst nuclear disasters that we've had resulting from power plants. As far as number 6, this happened in the Soviet Union. So it was not fully understood until much, much later, because the Soviet Union, dramatically, chomped down on the knowledge and information, etc. A number 5 is an accident with wider consequences. 3 Mile Island, which we'll talk about that. Our own Santa Susana nuclear facility here on the end of the San Fernando Valley, which started in '59, and you could argue is maybe still playing out. That kind of stuff, right? So that's more of a 5, and then a 4 would be relatively minor, no significant impacts of folks. This is an alternative measure of the intensity of a nuclear accident. So in contrast to that IAEA one, this is much more objective. And so this just looks at the amount of radiation. So it doesn't speak to countermeasures and ecological stuff and whatever. So these guys all have roles, but in that context, using these scales, we get a little bit different rating, right? So Chernobyl comes out the worst or tied for the worst in both scales. So everybody says Chernobyl was, very, very bad. Whereas the IAEA says Fukushima was also that bad. Actually, in terms of the amount of radiation release, 3 Mile Island is a little bit worse than Fukushima, etc. So we can get into the weeds, but I'll just tell you guys there's a few different ways of saying how bad was that particular event. Okay, let's talk for a second about Chernobyl. So does anybody? You guys were no, you guys were alive then. Does anybody watch the HBO documentary on Chernobyl? 1, 2, 3 people have. Okay. So basically, this was basically my birthday weekend, and I was getting ready to go out with my dad or do something. I can't remember what we were going to do. And all of a sudden, everything started getting weird, and people are like, "Hey, there's something going on in the Soviet Union," and we're like, "What?" And it started to trickle out, And it turned out, it took a while for the specifics to come out, but it turned out it was this. And so this is Time magazine, which you guys don't read and doesn't really exist as a magazine anymore. But this was the cover, right? So this was a dramatic thing. So Chernobyl is inside Ukraine, which we'll get to in a little bit, which at the time was part of the Soviet Union. So it was one sort of big territory. And what happened was the design of the reactor was stupid. The design of the reactor was not smart in any way, shape, or form. And so essentially these guys had a power surge, and that power surge led to the water. And so this was okay, so I probably should have put this in earlier. I have it later. But basically, how nuclear power works is fundamentally different from nuclear bombs, if all goes well, right? So nuclear bombs were about like, boom, instant, huge amount of release of energy, boom, very dramatic, right? Nuclear power is about the controlled release of that energy. So nuclear power has some radioactive material, and if we just leave it alone, it's going to start to boom, 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 get warmer and warmer and hotter, and radiation's coming out. And so we have some manner to slow down that release of radiation, usually in the form of what we call control rods. So we put structures inside that radioactive mass, and that slows down the reaction. So by adding in the control rods or removing those control rods, we can change the temperature. Essentially, all these crazy billion-dollar plants, all they're doing is boiling water. No different from if you had an oil plant or a coal plant or a natural gas plant, and you lit the flame and you stuck it underneath a tank of water and the water starts to boil. That's all we're doing. So we're using the heat that comes as a consequence of that ionizing radiation interacting with water or other molecules, and we're turning that heat into thermal energy that turns water into steam. That steam turns a turbine, etc. Okay, so essentially that water that we use to convey the thermal energy to the turbines essentially flashes to steam, no longer becomes liquid, and then it just blows off the top of the reactor vessel. So blows off the trash can lid, you can think of it as. And then that leads to, and these are graphite reactors, which we won't go into the specifics here, just suffice to say, once a problem gets going, very hard to stop. Okay, once the reaction starts running away from it, very, very difficult. And so that was sort of the physical thing that was happening. And then the operator control. So what the humans could do in the loop was very, very weak and poorly designed. So the design was inherently not super safe. And then whatever we could do to intervene wasn't really rigorous. And so that leads to Chernobyl, and it's a huge problem. So basically it's a graphite reactor. In the initial days after, most people that die are the firefighters, the first responders that show up. And because this thing is hot and heating, one of the first things to do is to try to cool it down, right? And so they call it firefighters that squirt basically water on the thing as if it was a traditional fire or something. And this leads to a huge amount of radioactive release. Again, this is the worst such accident ever in the history of the world. And so something on the order of 5% of the physical core gets volatilized and turns into particles in the air and moves around Europe, right? And so everybody's freaked out. And one of the things it severely does is it deeply freaks people out in terms of the confidence in this type of energy production. And people are like, wow, this is super scary. I don't know if this is worth the risk of producing power from these guys. Other than those, and again, this is complicated by the Soviet Union, not transparent, not giving data out, not you can barely get information out, and then everybody's scared, and then they immediately order an evacuation of the neighboring community. So then everybody's moved, and so there aren't even as many people that are there to observe what's going on. So it was a huge information black hole. So the UN forms a committee to figure out what's going on, and long story short, an increase in cancer is what we think was going on for the most part. So not a whole lot of people died immediately other than those immediate first responders. But essentially we see an increase in the background rate of different types of cancers. One of the reasons that thyroid cancers is one of the ones that we focus on is because your thyroid accumulates iodine. Iodine is one of these short-lived species, and so it's a relatively easy one to look at. But essentially, there's little detectable increase overall, right? So there's some, but little. And so this gets into the issue, especially when we evacuate this whole population, move them around. So just as we've seen from these other disasters, just moving around itself is stressful. Just having a wildfire come through your town can make your kids depressed, can lead to domestic violence, there's all these other things that are going on. So it's hard to say, was that a radiation thing or was that a something else thing? And then just all that stuff. So it's very hard to find proof of dramatically increased, for example, cancer risk. About 1/3 of a million people get displaced, get evacuated. And are still evacuated. There's some people that have moved back, but the vast majority of these. So if there's a whole disaster tourism thing that has spun up, not during the war, of course, but before the war, you go to what's now modern Ukraine, and you can go tour the facility, and it's like a zombie apocalypse, right? It's like the buildings are there, the kids play structures are there, and there's just weeds and things growing up through them, and it's fairly creepy. And it's a big area of research. So some of my colleagues actually work on this. So on the effect on birds and other things. And it's become a major source of research, particularly for what happens if humans are removed from a landscape. So how exploited species can recover, deer and things like that. It seems pretty clear that the greatest damage is on our perception of energy, et cetera, not so much the outright killing of a bunch of folks per se. The structure was so damaged by the accident that you couldn't just turn the valve off. We had to build something. So we built a tomb, which is known as the sarcophagus. Initially, we poured a bunch of cement and did like a temporary kind of thing. But then we came in and designed a huge, massive sarcophagus, which is a container that was built actually on rollers. We built it away from the nuclear site because it's still so radioactive. And then once it was constructed, we rolled it into place on top, over the former nuclear power plant. Before the war, which we'll talk about in a little bit, before the war, in effect, we had a 30-kilometer no-go zone around this place. And so this was essentially, in effect, a wildlife preserve, right? A biological reserve. Yes, there's a lot of radiation. Yes, it's messing with genes and stuff, but it seems like that's way less bad than having humans live next to you. So many species have recovered, even in the wake of these relatively high radiation areas. And currently it's threatened by the fighting in Ukraine, which we'll talk about in a few minutes. Okay, next I want to talk about 3 Mile Island. What do you guys know about 3 Mile Island? Or what do you remember?
I heard that it was like blown out of proportion and wasn't as bad as a lot of people seem to think, but also it might have been. I'm not really sure.
Yeah, definitely. So definitely the public fear. We'll talk about why that was, but the public fear versus what actually happened, I would say we were very lucky. We turned out to be very lucky the way it played out. But nevertheless, yeah, there's definitely, just like with Chernobyl, there's this sort of public narrative and there's what actually happened, right? Which differs significantly. Anybody else? Any other 3 Mile Island impressions or thoughts? No? Nothing. Okay. So this is in the 70s. This is, we're back east, this is in the US. And essentially, this is a reactor, everything's running fine. And then early in the morning, alarm trips that, hey, there's something amiss, right? And essentially, a pressure relief valve sticks open. So these guys think it's closed, but it's stuck open. So they're trying to figure it out, and they're getting essentially mixed signals. So what was actually going on was the relief valve was open. And so this steam, so the liquid inside the vessel is venting, but they don't know it's venting, right? And so as it's venting, that means it's no longer there. That means there's less water, and so there's less thermal mass and all this kind of stuff. And so they essentially, because of this more primitive instrumentation and all this stuff, they basically accidentally shut off the ability of the system to cool itself. Okay, so they unintentionally did the wrong thing. By 6:30, they figure out what is going, and they address it. But the water was so low, the water level, the coolant in the container was so low that the fuel rods start to leak. And they start to leak, and then that radiation starts to get out into the environment. And it gets into the containment building. And so that's where they notice now a radiation alarm start going off, kind of thing. And the worry is an explosion, right? So this is all happening, and if it's so hot and there's so much radiation, we can actually get those H2O molecules to split apart, just like you put electric current into a glass of water. And we could get a buildup of hydrogen, and the worry was that if that happens, the containment vessel, so the concrete garbage can over the whole structure could just blow off. And then if it blows off, then all that radiation is just straight up in the atmosphere, right? And it's straight to the regular air, and it can blow onto the neighboring town and all that kind of stuff. So they evacuate about 150,000 people. They order everybody, get out of town, go. So go far away, leave right now, don't grab your wedding album, just go, right? So huge fear. You can imagine what happens if all of a sudden you're told, especially if you think this is a safe thing, right? It's not even like a wildfire where we can see the thing. It's just people say, run now. And the images you have in your head are Godzilla and mutants and horrible suffering in the wake of a nuclear bomb, right? So people freak out and they bolt. So thankfully that doesn't happen. And there's definitely radiation release, but not of, the core didn't melt down in the atmosphere and do all that kind of stuff. So the takeaways from this were, again, we need way better training, and we need way better planning for how to deal with these disasters, better checklists, better all this kind of stuff. So again, nobody was killed, nobody was injured here, nobody suffered, as far as we can tell, nobody suffered increased cancer rates or anything like that. But it dramatically struck a dagger into nuclear power plants in the U.S. In '96, a court case was finally dismissed, where the judges said, "Hey, there's no evidence that that people that were in the area that you were exposed to any kind of real problematic level of radiation," which is a good thing. I mean, that's a positive thing, right? And it led to all this improvement and stuff. But here's the real kicker. The real kicker is this. The real kicker is Hollywood made a movie called The China Syndrome. Has anybody seen China Syndrome? You guys should watch China Syndrome. So this was a fictionalized story, a fictionalized account, but it came out in theaters 12 days before 3 Mile Island happened. So as this disaster is playing out in the theaters, is this, very, star-studded Hollywood special effects, all that kind of jazz going on about, something that seemed very, very similar, right? And it was what you would expect, the nefarious, evil power plant people and they're keeping the truth from the public and all that kind of stuff. And so this is out there. So this is in the minds of people's minds, and then you start seeing this. So then protesters start showing up, and so the film was named China Syndrome for sort of a similar situation. We have an accident that gets out of control. The coolant ability is robbed from the plant, and it starts a meltdown. And so the lore is that, oh my God, this core will just be so molten and so hot, it'll start burning into the earth, and it'll burn all the way through the middle of the earth to China. That's where the name comes from, the China Syndrome, right? So obviously that's all farcical, but this was real. So people had a very clear visual in their mind. Even if they didn't know anything about nuclear power, they had images. So newspapers would run pictures of the movie in the news stories about the disaster, right? So this just takes it up beyond anything we'd seen before, right? And so that really has a huge effect. I think the clearest way to see this is right here. So this is up to a few years ago. This is nuclear power in the US. And this is potential capacity, and this is what we actually end up generating, and design capacity and what we actually end up generating. And if you look at this, starting in the 50s, so we were going to put power plants all over the place. We had a plan to put a power plant on Topanga Canyon. We were going to put nuclear power plants all over the place, right? That was the original plan. And so when you look at their original design, as we start in the 50s, they start to go up, and we're going exponential here. Whoop! We're just on a big rocket ship. And then what happens is 3 Mile Island. So 3 Mile Island kills, in a very real sense, the nuclear power industry in the US. So people are like, yeah, no, don't want this anymore, done. So that one gray rhino had a huge impact on all kinds of other things. Okay. And I'll just have you know, this is not old news. So just last year, Microsoft announced a deal with the utility that controls 3 Mile Island, which had shuttered it, which had mothballed it. It was done. It was past its day. So that reactor that melted down was messed up, but we had other reactors there. They were still running until 2019. Then we started shutting it down. Then we officially retired it and mothballed it. And now to take a nuclear reactor to fully get rid of it takes many years, decades probably, to disassemble the plant and take care of all the radiation and deal with all this kind of stuff. So they were in the middle of that. And then now Microsoft is like, oh my gosh, we need more energy. We need more energy for Bitcoin. We need more energy for AI. We need more energy for all this kind of other stuff. And so Microsoft enters into an agreement with the utility to reactivate 3 Mile Island. So something we thought was completely dead, way beyond its design life, way beyond its design life, is potentially being resurrected. So it's not running right now, but they're working on beginning to get it back into shape that it could be turned back on again in about the next 5 years, is the idea. So 3 Mile Island, which in years past, I was like, this is a history lesson. It's back, and it doesn't seem to. It's like the undead, right? It's the zombie that keeps coming back. And so one thing we need to talk about when we have these accidents, these disasters with does it make sense? Any questions about that stuff so far? Everybody's been very quiet today. Questions? Making sense so far? Okay. So one thing we need to ask is this a feature or a bug? So are these accidents, it just sort of happened, couldn't have figured out, or is it more of a design property of these things, right? And so one of those examples that we can see that I think most clearly is the Fukushima disaster. So now we've jumped forward. Now we're 2011. Now we're in Japan. Japan, awesome country, cool stuff. All kinds of really cool culture and stuff, but not a huge amount of resources, right? Relatively small islands. So they were one of the countries that had embraced nuclear power quite a lot. They don't have a lot of oil fields. They don't have a lot of coal deposits, right? So this was one of the things they leaned into hard. So this particular, so their industry starts in the 60s, so a little bit after us, about a decade or so after us, but nevertheless pretty soon. And leading up to 2011, it's producing about 1/3, or it's meeting about 1/3 of the Japanese electrical needs in the country, the nuclear power industry. The Japanese are planners, and they plan for this stuff, and hey, we're going to do this, and we're going to use what's called design basis for the basic accident, so that this will be robust. Again, this is, as we know from our earthquake discussions, this is on the Ring of Fire, the plate tectonics, the Pacific, very, very active volcanoes, very, very active earthquakes. So they're designing this to deal with the shaking. And so this is what the plant looked like before the disaster in 2011. And so we have a total of six reactors, 2 of which are not functioning as because they were they had them turned off, and then 4 didn't have the fuel in it, and so 3 of these guys weren't operating. So we only have 3 of our units working. But have a look; it's right on the coast, right? So it's right next to the water, and in fact, many of our nuclear plants are on the water. Our 2 nuclear power plants in California, one of which is mothballed, they are located at the water's edge. One in San Luis Obispo County, one in Orange County, because we want to use the thermal mass of the ocean as the coolant. So just to be clear, we don't use ocean water as the coolant. We suck in ocean water and have a heat exchanger, and so we're using the temperature of the ocean, but we're not using ocean water. So it's not as if, so no ocean water under routine operation would ever come out radioactive, right? So it's a heat exchanger that uses it. But there are impacts. Obviously here they have an embayment to keep the water under control. And if anybody takes coastal, we'll get to go see this in the fall when we go up to see San Onofre. So if you guys want to go see a nuclear power plant, you should come with us on the coastal class. And that's one of our stops. We routinely do. So this area out in the forebay here is making sure there's no waves, and they can suck the water in, and then they can discharge the water, etc. So that's a desirous thing from an engineering perspective. Turns out that was not a good thing from a tsunami perspective, right? And so this is another water. Yeah, we can skip over this. This is the reactor. Okay, so 2011. The earthquake happens, and as we've also learned in our class, a lot of times we have multiple disasters, a thing that plays into a thing, that plays into a thing, that plays into a thing, and that definitely is what happened here. So first and foremost, we have this earthquake that was offshore, that was very strong, very dramatic, very damaging in and of itself. That was a problem. But then it started this huge tidal wave, right? So that displacement of the seabed leads to this big wave propagation. This was, at the time, I think still is, the 4th largest earthquake recorded in and around Japan. And so a huge tsunami wave that is 50 feet high comes and essentially inundates this plant. And it leads to the nuclear disaster. So much so now that we don't think of the earthquake, we think of Fukushima, the story that happened in 2011, as a nuclear accident, not necessarily an earthquake or a tsunami accident, right? So the earthquake begets the tsunami that begets the nuclear accident. And so the main problem here was and we'll see this again when we get to Ukraine, all of our power plants need to operate or be able to operate if there's a disaster, right? And so normally, under normal operations, the electricity to run the instruments, to run this, it comes from the power plant, because you're a power plant, right? Making electricity. But if something goes wrong and you lose that ability to generate electricity, you need a power plant. So all of our nuclear power plants have emergency backup power plants just so they can do their stuff. The problem with Fukushima is they put it in the basement. So their generators were below sea level. So when that tidal wave came and swamped the area, obviously physically it broke stuff and damaged. So in and of itself, that would be problematic. But then it took out the ability to run the pumps, to run the systems that would cool the plant down. And that's where we get into this runaway thing, and then things get out of control and melt down and then implode and all that kind of stuff. So this is Fukushima today. It's obviously, it doesn't function as a power plant anymore. It's messed up. It's still leaking tons of radiation. It has a big, huge, giant slag. The melted core is still there. And it's on the order of probably several decades that we'll be dealing with trying to get this core under control. Just like with 3 Mile Island, we see this. We see stuff like this immediately comes out. And maybe you guys are old enough to remember this. Does anybody remember Fukushima? Not quite. 1 or 2, a few. Yeah, you guys maybe were in grammar school or something like that when this was happening or something. I'm so old. But we saw a lot of this kind of stuff. And again, Facebook starts in 2007, and that's when all the crap starts to happen. And also iPhones, right? So this is the beginnings of social media, right? The early days of social media and all the poison that it does to our public discourse. And so this stuff starts propagating. So this was originally produced by NOAA, a science entity, but it gets sucked up, and on social media it becomes radiation. This is not radiation. This is a map of the potential tsunami wave heights, right, from the earthquake. But all this stuff immediately starts to get conflated, and people start to freak out, and all this misinformation starts to bing, 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 bing around. And again, simply saying the word radiation melts down a lot of people's brains, and they just get so scared and they get so freaked out. They just like, oh my God, oh my God, oh my God. And so it changes the conversation. So yeah, we could talk about that forever. And then you see things like this, and people are like, oh my God, the west coast of the U.S., we're all going to die. We're all going to die of cancer, all this kind of stuff, and it's not true. So there absolutely was atmospheric and oceanic release of this radiation, and it caused problems. But the primary, for example, if we look at cesium-137, the primary deposition is in the immediate area around the coastal site in Japan. And that's really where the main issue was. Again, like with our other accidents, people are evacuated. So people in the immediate proximity to the power plant are ordered to get out. There's great worry about contamination. Obviously, Japan is a major consumer of seafood. They're a major producer of seafood. So there's worry about foodstuffs. As of now, nothing to really be particularly worried about. However, also if you guys take coastal, we started our perception of seafood safety in the wake of the Deepwater Horizon, and then the wake of this, specifically to look at how people were freaked out. And many people, it's basically died back to background now, but many people were avoiding seafood from Asia or from Japan specifically in the wake of this, because they thought, oh my God, it's all contaminated, it's all whatever. Pretty much now, the food is not contaminated. There's a few possible exceptions with some of the critters that still frequent the area, like wild boar, but for the most part, there's no real major concern here. Even though, as I mentioned, radiation is continuing to enter the environment. One of the neat inventions in the wake of Fukushima has been citizen science. So if you want, who knows now with the tariffs, right? Let's probably go check just so I know. But if you wanted to get a really kick butt, if you want to get a really cool a radiation detector, you can get a cheap one that's kind of like not so good for like $200, $300. If you want like a really rock and roll one that does alpha, beta, gamma, like all that kind of stuff, you're talking like $500, $700, right? So not $1 billion, but still that's kind of pricey, right? We don't all have $500, $700 lying around, right? And so one of the questions was, hey, how much radiation is getting around Japan? How much radiation are these different communities exposed to? And it was just expensive. So what several groups in the US, and then it became an international effort, got together, and they basically designed this, which is a citizen science radiation detector. So it still costs a little bit of money, but it's on the order of tens to $100, you know, kind of that range. It's not hundreds of dollars or thousands of dollars. And they got cheaper, and as they mass produced them, they got cheaper and cheaper and cheaper. So now you can get one of these. So this allowed the public to do citizen science and to go out and say, hey, what is my radiation exposure? And you could report your location, just like we do with Purple Air and other things. And so, and in fact, I used to take students in New Orleans. When we used to have a faculty member who's now left to become a dean at another university, when he was here, a chemist, he did a postdoc in Japan, and so he would every other year take students to Japan. And then when Fukushima happens, like, oh, we can't go. I'm like, can't go, dude. You should totally go. You guys can help out with stuff. And one of the things I suggest they do is that they take some of these sensors with them. And this, for example, is one example of some of the citizen science collected data. So again, the blue on the right is the ocean, the light blue is the ocean, and then we see the landmass. And so this is from this crowdsourced citizen, not government research or whatever, just general public, people mapping out. And so the hotter the area, the more the radiation. So and this nonprofit now still exists. You guys could get some of these, and you guys could just have them in your backyard if you're curious as to what your background radiation exposure is, etc. Okay, we're about to shift gears here. So we could talk about San Onofre, which I'll just say this is down in coastal Orange County. It is shut down. So it is shut down and will no longer go. I could tell you the whole story if you want, but we'll just skip it. We'll just suffice it to say it was getting near the end of its life. They thought they would replace, so that they replaced some parts, and there's a big lawsuit still being played out. It's unclear what happened if the Southern California Edison gave them the wrong standards, or the people that made the replacement parts made them to the wrong tolerances. But long story short, the stuff wasn't working right, and there was some vibrations going on as the plant was operating, and we started to get some potential release of radiation. So they stopped it and basically just said, okay, it's getting too crazy. We're just going to shut down this plant. So when this one shut down, we were left with one nuclear power plant in 2013. We were left with one nuclear power plant. That's Diablo Canyon. Again, if you guys take my coastal class, we'll go up and see this in the fall. So this is in San Luis Obispo County. Just like everything else we thought was dead, so this goes. I can, again, talk to you for hours about this. You can watch some videos about previous trips that went up there. And all this kind of stuff goes. And PG&E is Pacific Gas and Electric. This is the utility. This is the extreme southern end of this utility's territory. It's almost into Southern California Edison's territory. They basically say, hey, we want to re-up our license. The way nuclear power plants work is you get a license so you can operate for a certain number of years, usually like 40 years. And so they were getting ready to renew this, and a bunch of environmental groups are like, no, we don't want nuclear power. So in a very surprising turn of events, in 2016, PG&E said, okay, and this never happens. They're like, okay, we're done. In the middle of this, the hearings to get the renewal, and because you have to get state permits and federal permits, and it's a very complicated process. They just kind of said one day, F it, no, we're done. And nobody had any idea they were doing this. So they said, yep, nope, we're terminating our application to extend our lease, and when 2024 comes, we're just gonna shut the whole thing down. And environmentalists are like, what? And they're like, woo! And their whole community went, wait, this is a major job employer. We get 9% of California's electricity from this one plant, right? And so whatever we think of nuclear power, this is carbon emission free, right? And so as we're transitioning to all of our wonderful solar and wind and renewables, right? They don't all blow all the time, so we need some what we call base load. So this is one of the key parts of our base load of electricity, like midnight and when it's stormy and all this and that. So suddenly we were going to lose that, and people freaked out. And so basically it came back from the dead, and in 2022 we had a bill introduced and into the state legislature that basically said, no, we're going to keep it operating. Essentially, we gave a loan to this utility to keep it going. And the reason why that was important was because All nuclear power plants in the U.S. rent their fuel. No power plant in the U.S. owns any fuel, any nuclear fuel. The U.S. government said, this is all ours. We'll make it for you. Well, you can rent it from us, but you run it in your plant, and then when you're done, you have to give it back to us because they don't want nuclear proliferation. They want people making dirty bombs and stuff. So that takes about a 2-year order. So if you want, it's not like getting an In-N-Out burger, right? Or maybe it is. It's like the world's longest In-N-Out line, I guess is maybe what it is, right? So you're like, I want that, and it just takes like 2 years to get to the front. You're like, oh my God, I'm so hungry. And so if this had not been renewed, there would be no way to continue making power. So this was the very last minute they could make an appeal and still put an order in to have enough fuel that come 2024 they could keep operating. And so that's where we are now. So they're planning to operate at least till 2030, maybe a bit longer, with the idea being that this will bridge us to where we have more battery storage. So that we can sort of time shift our solar and other things. So that's Diablo Canyon. That's what it looks like. This is the forebay. This is where they suck in the water, et cetera. And so most of our reactors are in China. So now most of the new reactors, most of the added capacity in the last few years is happening in Asia, specifically in China. And so the other thing I'll say before we turn to talking about the disaster, what's going on in Ukraine, is most of our power plants are very old. This is the age of our power plants. This is from a couple years ago, but it's still pretty right. So this is 0 years old, 1 year old, et cetera, up to about 50, right? Almost everybody is old like me, right? And so that's a problem because these plants are designed to be, like about a 40-year max lifespan. And we're not talking about, seaweed wraps and, Gwyneth Paltrow harmonizing sounds, right? This is ionizing radiation. So the very fact that we're operating these plants, the containment vessels, the fact that they're around radiation changes the structure of the material. It makes concrete brittle. It makes steel brittle. So it's not just like I want to keep operating. Like there are just some physical constraints that if we want to keep operating after about 40 years, you need to physically replace things. You need to put in a new tube, a new turbine, a new this, a new that. So it's totally non-trivial. It's a very important thing. You can't just say, okay, well, let's do it 5 more years. Let's do it. At some point, stuff's going to physically break and get us into trouble. Okay, so that's the setting. I want to next talk about Ukraine, but why don't we take a quick 10-minute break?